For example, if you wanted to calculate the force on this piece of material that's being submerged, if you came to this point B right here, the pressure, or pounds per square foot or Newton per square meter, would be the density of the fluid times its depth to that point, and this pressure is acting perpendicular to the surface. Similarly, down here at point C and point D, since they're at the same depth of Z2, they'll have the same pressure of the density times the depth, and both of these are acting perpendicular to the surface where they are. While we're talking about the phrase, for example, I'm going to give you a bonus Latin lesson. Sometimes when you read a paper or you're reading a book, it'll have e.g., and other times it'll have i.e. E.g. is an abbreviation of the Latin phrase exempli gratia, which translates for example, and i.e. is an abbreviation for id est, or that is. And easy to remember which one is which is that e.g. starts with e, that stands for, in my mind, example, so for example, or I often will think e.g. example. I know that's a little funny and weird, but it helps me remember. E.g. means for example. And I.e., I think of the I standing for in other words, or that is. That's how I think of those two abbreviations. Here's how to analyze fluid pressure on a flat plate with constant width. That's important. The top edge of the plate is at a depth of Z1, and so everywhere along that width, the pressure will be gamma times Z1. It's the density times the depth. And at the bottom, it has a depth of Z2, and the pressure will be gamma times Z2. And again, the pressure is constant along this width. And remember, we want to get the total volume of this weird, let me see if I can trace it, trapezoid prism. We're trying to get that volume. And what we can do is we can take a slice, like a slice of bread. So let's say this is a weird shaped loaf of bread, and we're going to take a slice like this. The slice of bread has a volume of the height, gamma z, okay, which we're calling the pressure. The volume is the height, pressure, times the width, b, times the length, dl. And what we can do, here's that slice of bread over there at the top edge. Here's that slice of bread here at the bottom edge. And we have all these different slices of bread that are getting taller because the pressure is not constant. But this volume will be that dl times the height, which is P1, times the width, B. This is how we get these loads that are linear with respect to length. This W1 is now pounds per foot because we took the pounds per square feet and multiplied it by the width. And then what we're going to do, we know it's linear because the pressure is linear with depth, and then we can solve this. This problem here is like the kinds of problems we have been doing where it's pounds per foot. To summarize, we changed the pounds per square foot into pounds per foot by multiplying by the width of the plate, B. But what if the plate is curved? You can get the pressure here, okay, the bread slice. So you get the depth times gamma to get P1 and multiply by the width, and that's W1. You can get the bread slice down here. You get the depth to that point D to get P2 multiplied by the width. But because the plate is curved, the depth is not changing linearly as you travel along the plate. Okay, so Z, the depth, is not changing linearly as you go along the length, and so you get that this pressure distribution is not a straight line from the front edge to the back. It's going to be some horrendous integral. This will be terribly difficult. You don't want to have to deal with that. Instead, what we're going to do is take our free body diagram to look like this. We're going to take this piece of water. Okay. On this horizontal surface, you know the depth, and it's constant. This depth is constant, and you can get this pressure here. Again, multiply by the width B, so pressure 1 times the width B, and this is constant. Okay. And you can get the resultant of that, F on the top. And on the side, it is linear, so you get this bread slice here because this vertical surface is linear. You get this bread slice here, which will be the pressure at the bottom times the width, the pressure at the top times the width. And this is linear, so you can connect it with a straight dot. And you get the resultant of that trapezoid. Likely you'll break it up into a rectangle and a triangle. But anyway, you can get this resultant. And finally, the other load acting on this is the weight of the water in this piece in here. And all three of those forces, if you add them up, this, and that, are all the things that are acting on that curved surface. This is still difficult, but not impossible like the first one, so I'm going to give this one a smiley face. Maybe not quite smiling, but you can do that one if you work hard at it. Finally, what if you have a flat plate? It's not curved, but the width is varying. Well, you know the pressure P is linear with depth. However, and remember W is B times the pressure. And so you can get this, it's linear with depth. However, in this case, B is not constant. We had that as constant. So the W at any given depth is the pressure at that depth times the width at that depth. And additionally, that pressure is given by the density times Z. You can do this. You just have to integrate B of Z times gamma Z to get the total load on a flat plate with a varying width. The main points are that force is pressure times area, and that pressure is changing with depth linearly. And in this case, the area is changing with depth, and therefore this is what you have. And I can even put that the pressure at Z is gamma times Z times the area as a function of Z. And if you're integrating along the length, it would be gamma Z, the width as a function of Z, dl. I'll do a few examples to show how this works, and then hopefully on Thursday you can do some problems with Dr. Erickson.